thank you for the invitation. I think this is only my third time in Vienna. I've been at the ESI once before and once in Vienna independently. And Standa, you will need reading classes soon. So it's a sure sign when you have to read everything with your hands extended. Then it's time to get reading classes. Okay, so I'm going to give a Beamer talk. There's this phrase that old dogs do not learn new tricks. I learned to use overhead projectors, but they have taken all of them out. So now the next stage has been to try to use beamers, and I'm very good in that. I already can get the date on it. But I figured out how to get the correct date. That's by latexing it in the morning of the talk. But I sent my PDF yesterday, so I decided not to switch it. Okay. This computer-related things and techniques is not really for me. My phone crashed last week, and I was able to delete most of my WhatsApp, which it should be technically impossible. It's one of the easiest, the most difficult things to do, but I figured out how to do it. Okay, so I'm going to talk about homeomorphic Sobolev extensions of parametrizations of Jordan curves. And see. So what I'm doing, I'm reusing parts of my slides from 2018. And that's because then the story basically started for me. And I have updated the slides based on what I've been able to do since then. Okay, so the starting point is that we take a parametrization of a Jordan curve in the plane, and then by the Jordan-Schoenflies theorem, we know that we can extend this homeomorphism from the circle to a homeomorphism of the entire plane. And now my question is that since we have a homeomorphic extension, let's look at all possible homeomorphic extensions and ask what is the best regularity in this class. So it's like, you think about it, the boundary value problem. We are just given some homeomorphic boundary values, and I try to find the best possible extension. The reason I started to think about this was that I wanted to understand if every Jordan curve in the plane is the image of the unit circle under a global homeomorphism which has integrable distortion. So by distortion, what I'm basically saying that I want to look at a homeomorphism F, which is W11 locally, and then I look at the differential, and I ask that the Jacobian, if the Jacobian vanishes, then the differential has to vanish as vanish also. Let me look at orientation preserving ones so that Jacobian will be non-negative. So this inequality by itself is only saying that if this is 0, this should be 0 also. If that's the case, they can solve for k of x. And by saying integrable distortion, I'm asking, can I find an extension so that k is up to some degree integrable? And the answer is that you cannot expect the k to be locally in L1. It's easy to give counterexamples to that. But could it be that you can always find an extension which would be W11 locally in the plane, and the distortion function would be in LP locally for OP strictly less than 1. So that was my original motivation for going into this, and I was sure that this holds. So you can always find such an extension. Okay, and now how was I going to attack my problem? So I take the unit disk, here's my Jordan curve. Okay, and let me first try to get some homeomorphism onto this. So I want to find a homeomorphism of the entire plane that parametrizes the Jordan curve and has nice properties. So a natural thing to do is to take G, the conformal map of the exterior, to the exterior. So now I have W12 locally up to the boundary, right? By the Osgood-Kara-Theodory theorem, this G extends to a homeomorphism from the circle onto the Jordan curve. So if I can extend this map, this homeomorphism G goes from boundary to an interior homeomorphism, which is W11, I'm almost done, because then if I can extend, I should be able to extend locally piecewise affinely, so that the extension is locally affine. And once it's locally affine, then I can modify it so that it stays in W11, and I can improve on the distortion. And the reason you can improve on the distortion is only if you only ask for integrability with decrease strictly less than 1, then you can concentrate the distortion in a very small set. And since the power is strictly smaller than 1, once you compute, you see that, okay, you end up getting something which is very small. So it seems that I should attack this question. So let's see what was known originally. If in the case this Jordan curve here is a convex, the interior is a convex domain, and if I take the Poisson extension of the boundary values, then the Radok-Choquet theory tells me that I get a diffeomorphism of the disk onto the domain. And since this is harmonic, you expect that this has the smallest energy. It should at least have the smallest L2 energy. And if it has the smallest L2 energy, it's probably as good as you can get. Okay? And there's actually a theorem by Greg Verkota from 2007. He proved that if you look at circle homeomorphisms, so you go from the circle to the circle, you take the Poisson extension, then you get LP derivatives for all p strictly less than 2, but not necessarily L2 derivatives. And this is the best you can get. And it's easy to see that you cannot get L2, because if you take your map, I goes from here to here, and what you can do, you can reflect on this side, and you can reflect on that side, and what you end up getting that if you have your extension, say W12 extension, you can get the W12 extension in a larger set, a homeomorphic W12 extension. Right? But if you take a homeomorphism that has L2 derivatives, it has a modulus of continuity. And the modulus of continuity is of the type 1 over square root of log of 1 over t. Right? So if you can extend to W12, then phi has a logarithmic modulus of continuity. So it cannot work for all phi. Okay, so this is what is behind the negative direction that you cannot get L2 derivatives. And then a little bit later came the result in a paper by Dadeus, Gavin, and Carlo, and they proved that you actually get L2, but weak L2. You cannot get L2, but you get good weak L2 estimates. So it's precisely at this logarithmic type of moduli of continuity that destroyed the case. And actually, this was not only for circle homeomorphisms. You can do this if you have a convex target. If the interior of the Jordan curve is convex, because then the Poisson extension works nicely. And then I started to work on this around 2017, I think, and think about this problem. And then I worked with a couple of my students, Zhuang Wang and Haiking Xu, and then another student of mine, Yi Ruya Zhang. There is a story behind his name. The middle part is not part of his name, so he's really Yi Zhang. And when he wrote the first paper with me, I asked him, how do you know how many Yi Zhangs are there in MathSciNet? You should check. It's a non-trivial number. So do you want to be Yi Zhang 37? Or are you going to change your name? And then he said that, but if he changes his name, he would have to talk to his mother. And mother might not like it. I said, you don't have to change it, but only for mathematical purposes. That you start to publish under a pseudonym in mathematics. And then he suggested that he could try Yi Petteri Zhang. But then he came to the conclusion that this will not work out because then he couldn't pronounce his own name. And then he tried to find a Chinese version of Petteri, and he went for Ruya, which has some meaning. And I asked him, is it now clear that you are unique? And he told, yes, this name is unique in Chinese. Okay. Then Alexis Koski and Jani Onninen, who are going to talk on Wednesday. Actually, Alexis is going to talk about the things that extend partially what I'm telling today. So there are some aspects that of the problem that I'm not considering at all. He will talk about some of them. And then there is work by Ondra Buchala, who is our joint PhD student of Standards and Mind, together with Jarmo Jääskeläinen and Xilin Xu, who is also a PhD student of mine, that I will mention towards the end. So I'm now only going to concentrate on the case where I try to extend to the disk. So I have a homeomorphism from the unit circle into the plane, and I want to know when can I extend it nicely. And first comes the bad news. What I expected is false. There is a parametrization of a Jordan curve that does not admit a homeomorphic W11 extension to the disk. Okay? So I expected no such example to exist. And but Yi, I told Yi that could it be true that you can always extend, and a couple of days later he came back to me and told no, that he has a counterexample. And then Yi went to Bonn as a postdoc, and which more towards PDs, worked under Herbert Koch, and after that he was a postdoc of Figalli at ETH, and he's now with the Chinese Academy in Beijing. So he's a rather sharp guy. And even not only this, even worse, you can choose phi to be the boundary value of a conformal map. So what I was trying to do here will not work. So you take an exterior conformal map, you cannot necessarily extend that. It doesn't kill my original question, because maybe there's some other homeomorphism you can extend. But this makes the situation very difficult because you do not know which homeomorphism to choose. The conformal one is the canonical one. The problem with the conformal one is that it's too good on one of the sides, because Now on the exterior, it would have bounded derivative distortion. So the k would be a bounded function, and it would have L2 derivatives. So what one should do is to make that map worse so that it's easier to extend to the other side. Okay, but since this here, it's not true always, then you ask the question, when is it true? What do you need to know? Is it a property of phi, or is it a property of the Jordan curve? And I chose the direction of property of the Jordan curve, because if I want to use the conformal map here, I cannot choose the homeomorphism anymore. It is the one given by the conformal map. So I would like to have a geometric condition on this Jordan curve so that I can extend to W11 any boundary homeomorphism. And the first thing we did was to look at a very special case. These are called interior Kodak curves. And let me just draw you the picture. This is an interior Kodak curve. Right. Rectifiable boundary, no outward going cusps. Inward coming cusps are fine. The condition is saying that if I take 2 points on the boundary, these seem to be the problematic ones, then the minimum of the length of the two arcs that these points cut from the Jordan curve, the minimum length of this is no more than constant times the interior distance between these points, which is fine because the interior distance here is basically the same thing. Okay, so pictures like this are fine from the point of view of this definition. And then what we proved is that if you take an internal Kodak curve, then any parametrization of it can be extended to W1P for all p strictly less than 2. Okay. But then when I was looking at the proof, it seems that, okay, I'm ruling out outward cusps. So what about if I have a domain like this? No problem. This technique doesn't give it, but this is not a problem. Why? Because this is a cone that you have pinched. Just first map to the cone, open it. So think about that your map goes to the cone, then you can extend it, right? Because it's an interior Kodak curve. And after that, you do this. That's a Lipschitz map. And don't do it stupidly so that injectivity fails, right? So this domain is fine. So I conjectured that if the Jordan curve is rectifiable, you can always do it, but I was not able to prove it. I saw why it should be true, but couldn't get my hands to it. And my second conjecture was that if I rule out exterior cusps of all types, we should be fine. And that was the condition of a John domain. If you don't know what a John domain is, it means that you can put in a twisted cone to every boundary point. Twisted cone of a fixed size, right? So it's not infinitesimally small, but you can approach every point on the boundary by a twisted cone, and the twisting is controlled. So it's a bi-Lipschitz, there's a constant L and L bi-Lipschitz image of a standard cone that you can use to approach, access every boundary point. That's a way to think about the John domain definition. And that would basically be a version of this here, but the boundary doesn't need to be rectifiable anymore. It could be a snowflake curve. And I'm just saying that, okay, no outward going bubbles or cusps. Okay. Both of the conjectures are true. The rectifiable Jordan curves case was proven by Alexis and Jani. And the John domain case, we did together, myself with Alexis and Jani. So it looks very satisfactory, but I had already started to try to prove conjecture 1 before we started to work together on the problem, and I already knew that this is not the correct assumption. The statement holds under weaker conditions, and I was sure that if the conformal map onto the interior domain is uniform Hölder continuous, then you can extend. And the point is that that rules out exterior cusps, but it doesn't rule out exterior pinching. So you could have bottlenecks, but there's a control on the bottlenecks, not arbitrary bottlenecks, but sort of like polynomial type of behavior of the cut. Say that if you make a bubble of size R, the maximum you can pinch it at the bottom is like, say, R squared. There's some power that works for all the bubbles. That should still be okay for my problem. Okay, so now I have to talk a little bit about the hyperbolic metric. So if in your complex analysis course, you have probably seen the hyperbolic metric in the disk, or hyperbolic distance in the upper half plane. In the upper half plane, it's the path metric obtained by minimizing integrals of 1 over imaginary part of z. Okay? So you can explicitly compute it. And this metric is conformally invariant. So in the disk, you also have explicit formulas. And for general domains, simply connected domains, you define it by conformal invariance. So there is a metric. And what I'm saying here is basically a tautology. Your map is going to be uniformly Hölder, conformal map is going to be uniformly Hölder continuous precisely when the hyperbolic distance in this, say, Jordan domain grows at most like a log. Constant times the log. Now think about the upper half plane. If the density is 1 over distance to the boundary, you get a log. So this is the best possible boundary you can have. It's only issue of this constant in front of the logarithm. But this is equivalent with the uniform Hölder continuity of the conformal map, modulo the value of c and the exponent alpha in the uniform Hölder continuity. And to see that is equivalent, you obtain it with a little bit of work by using the fact that you know what the metric is in the disk, and just plugging in a log, taking roots, they come out as constants from log, right? No surprise. It's sort of natural that this, and I will come back to this. This has a geometric interpretation in simply connected domains. Okay. So now we come to the work of Jones and Makarov. What is the year? Late 80s, early 90s. This is an annals paper where they proved, among other things, that if you have this bound, then the hyperbolic distance to the fixed base point, which I call f of 0. Sorry, I didn't tell what f is. F of 0 simply means that take a conformal map from the disk onto your domain, and you look at with respect to image of the 0, because then the formulas are nice in the disk. So you can transfer the formulas from the disk. Okay. This guy is exponentially integrable. So how could it be true? Take an exponential of that. That's going to be 1 over distance, controlled by 1 over distance to the boundary, to some power. That indicates that you should prove a dimension bound. Answer is yes. This condition on the hyperbolic distance implies that the Minkowski dimension of the boundary is going to be strictly smaller than 2. Okay? Once you put these two together, you get the exponential integrability. But this is not trivial. So it's not that you just take the definition and write down something. This is pages of computations. There are two proofs, the proof by Jones and Makarov, and then a proof by Stefan Rode and myself, which deals with so-called mean porous sets. Okay, so in order to solve my question, it would be enough to prove that if the hyperbolic distance to a base point is integrable, exponentially integrable, then you can extend maps onto that domain. It turns out that much more is true. So I take my Jordan curve and I assume that the hyperbolic distance computed to a base point is in LQ for some q strictly bigger than 1. If this is true, then you can extend phi to W1p for all p strictly less than 2. Actually, there's even an extension that is in all W1p's. Okay. So the parametrization plays no role. What plays role is the curve. So this is now a kind of condition I was looking for here. So I have a geometric criteria that allows me to extend any parametrization. Okay? And now, this is shockingly better than what I expected, because I tried to prove, it would have been enough to prove that if something is exponentially integrable, I get my conclusion. Now I'm proving that if it's LQ for some q strictly bigger than 1, it already works. Can I push this even further? Before that, let's look at geometry. So if you don't like the hyperbolic distance, think about the path metric on your domain, obtained by minimizing integrals of 1 over distance to the boundary. That's a geometric thing. You don't have to think about the conformal maps. This is now intrinsic. It's an intrinsic condition on the Jordan curve. Okay? So you can replace the hyperbolic distance here by the so-called quasi-hyperbolic distance, which is obtained from this density. And now I have geometric criteria. Okay. Can I improve on this? No. There is a Jordan curve and a parametrization so that the hyperbolic distance to a base point is in L1 of the domain, but my parametrization doesn't have a W11 extension. So it's all or nothing, right? And this we had to cook up with by hand because the example by Yi didn't give this. Now his example doesn't have the property that H is in L1. Okay. So in mathematics, once you prove something, and there's always a new question, right? What is the question now? Are there domains which H not where? So there are domains with H in L1 for which you cannot extend. Are there domains with H in L1 from which you can extend? Yes, I can cook up such an example. So now what I'm doing with my student is trying to analyze where this breaks down. So assume that H is in L1. What is the additional condition you have to put so that you can extend? Can you prove that that condition is if and only if, right? I don't see any hope in this, but I have sort of a conjecture of what could be true, but I have no idea yet how to approach my conjecture. Okay, there are many related questions that one could ask, and I only talk about one direction, trying to extend phi. What about extending phi inverse? What about extending the both sides at the same time? Can you cook up an extension which has a nice distortion once you put enough geometry on the domain? And Alexis will talk about part of that on Wednesday, right? Something. Yeah. Okay. There's a 3D question, naturally. I mean, I like to work with dimension 2 because they can get cleaner statements and you have more tools available. But of course, all this makes sense in all dimensions. But certain things are much more complicated. Okay. This is all I wanted to say, and it seems that I did reasonably well regarding the time.